I'm here today to talk a little bit about how we're using newer technologies to influence the way our operators make decisions, whether it's on Mars, on the space station, or even here on Earth. But a little bit of history before we get there. This is the first image that we've got from the red planet from Mars. And this is from Mariner 4 about 50 years ago or so. And back then, technology wasn't that fast, so we couldn't get the images back fast enough for the scientists to look at them. And so what they did was they got in the room, they took the bits back from the data and started to piece them together on a grid and then color them in, sort of a color by numbers. They were so eager to look at the pictures that this is what they did. And this is sort of the first glimpse we have of the red planet. Now, fast forward 10 years or so, we landed on the surface of Mars with Viking 1, and we took a little selfie of the rover's foot, as well as some of the sharp rocks around it. It's very impressive. Of course, over the course of the following decades, we've sent over a dozen spacecraft to Mars, resulting in the most recent one, the most recent rover, Curiosity, in 2012. And so these are the first images that came back from Curiosity. And although they're not glamorous by today's standards, it was a historic moment because for the first time, we, on the mission, were certain that the rover was safe and was communicating back to us. So these are, of course, the hazard cameras in front and behind the rover indicating where the rover was situated. So I think these images show, half a century of exploration on Mars. And it's exciting to look at history this way, but it's not how we explore fundamentally as a human species. Right? We explore like this. Right? We run around our environment, we immerse ourselves with the folks around us, and we share our journey with the people that we care about. So today I want to talk a little bit about why it's so hard for us to do the same for a place like Mars. Right? I think a lot of you guys know some of the background here, but I want to go in a little deeper. Right? So the first thing I want to talk about is what we covered already, was these 2D images. Right? These are the only assets we get back from Mars. The Mars rovers don't have fancy 3D sensors like the self-driving cars today. But from these 2D images, our scientists are obligated to reconstruct in their minds sort of the entire context of where the rover is situated, where they are, and where they want to be going the next day. The second issue we have is this. So I usually speak in front of school kids in classrooms, so I think this is one audience where most of you understand what that sound is. That's a 56K modem, of course, right? And back in the day, it took 30 minutes to download your favorite MP3. Our deep space network is how we communicate with everything in space. And although it's not as bad as a 56K modem, we don't have direct comms with our assets at all times. So if you average that out over the course of a day, you have about a bandwidth of a 56K modem. So not only do we have limited types of data that we send back, but we have to be very selective in the images that we want to send back because we can't send everything back. The third issue we have is this, and it's what gamers would call lag, and it's what we call time delay. Right? So if you play games, the latency of about 500 milliseconds is horrendous. And when we communicate with an asset on Mars, we're talking about 15 minutes of delay. Right? So what that really means is we can't joystick the rover, we can't joystick a lot of our assets. We have to take time delay into account for our operations. And oftentimes what that means is we only get one shot every single day to get the data back and one chance to send it a list of chores to do for the next day. The last thing I want to talk about is this, right? It's collaboration. It's something we take for granted, but it's something that we're doing today, this week. We're working together in the same environment, talking to each other, and having a fruitful discussion. Just digging into that a little bit more, most of our scientists on the Mars missions, they're geologists, right? So on Earth, they'll come to places like this and go out to outcrops with their colleagues and explore the environment. They'll take out their tools, they'll work with their colleagues, they'll chip out the rocks, and they have this physical context of where they are. Now, when we tell them to go study Mars, we take away all of that, right? We put them behind a small screen, we give them tiny images, and they're expected to kind of mind meld all that data, not only within them, themselves, but also with their colleagues all around the world, which is a very complicated task. So our team, I lead a visualization team at JPL, and our focus was, can we take these small images that we get back, the limited data sets that we get back from Mars, and create a more immersive world for our operators? So this is what Mars looks like today with our capabilities. This is the best 3D scene reconstruction that we have. Every single pixel in this render is real. There's no artist in the loop. It's all automated. This is running in real time in a game engine. So, what we're trying to do here is really lower the barrier of entry and the burden for our operators to understand the worlds that they're in. Just to go in a little bit deeper here, without getting too much technical detail, what we're doing is we're taking the hazard cameras from the rover, building up a depth map, colorizing it with high-resolution mass camera data, and then filling the gaps and the holes from the high-rise imager from the MRO orbiter. So collectively, we have the best image 3D model of Mars, which then we towel up and serve through multiple platforms. So you can see this on the web, you can see it on a VR, AR headset, and really it changes the way we do our work, because for the first time, our scientists all around the world, they can get up from the desks and walk around on Mars. And they can do that together with their colleagues all around the world, right? They can understand where they are today, where they want to go the next day, and make plans in this environment, right? Not on just some 2D tool. So, we didn't stop here, because every time we build something that's useful for our scientists, we want to share that with the public as well. So I just want to quickly talk about this tool we built called Access Mars. So we partnered with Google and used an open capability called WebVR to enable the same experience on a number of different platforms. So this works on your phone, it works on your laptop, it works on a VR headset. And it's curated for the public because we have our mission scientist, Katie Stack, that walks you through a number of key sites on Mars. So let's take a quick look.
On November 26, 2011, NASA and JPL launched the Curiosity Rover on its mission to find out if Mars has ever been suitable for life. Since then, it's taken over 200,000 photographs, used by NASA JPL scientists to create the most realistic 3D model of Mars ever seen. Today, it's yours to explore, on a computer, phone, or in VR, the real surface of Mars, photographed by the Curiosity Rover, now in your browser.
So that experience is live at accessmars.com, and you're free to try that later on in the day. But before I move on, I wanted to kind of show you what this experience feels like. I have a headset that later I can walk you guys through one at a time. But for the larger audience, I'll just show you sort of the browser experience. This is the operations tool for our, can we see my desktop here? Let's see. Close this. Yeah? Okay. So this is the operations platform that we use on the web. And as you can see, it's the same 3D reconstruction. Let me go my mouse here. But what you're seeing here is, I can pan around and move around very much like Google Earth. This is one of the latest sites on Curiosity. But everywhere I click on the environment, I get a list of raw images on the left side that indicate all the raw images that made up that pixel. And when I click on them, it overlays that 2D image on the 3D environment. So you get this perfect context of 2D and 3D. And so we're really trying to figure out, what's the best interaction on each of those platforms, whether it's web, whether it's mobile, whether it's an immersive experience. And you know, we can make annotations here. We can join discussions, whichever platform you're on, and really have this you know, engagement that we've never had before. I also want to show you a sneak peek of a tool we're developing in tandem with JAXA. Is the capability we have to reconstruct for Mars. We can do that for any remote environment, right? We can do it for small bodies like asteroids. We can do it for terrestrial locations. We can do it for space station, any place where we can't send a lot of humans. So we've been talking a lot with the Hayabusa 2 mission at JAXA to help them reconstruct Ryugu. Now, that data set's not public yet, but I want to show you what we've done with the previous asset, which is Irokawa from the Hayabusa 1 mission. And this is just, you know, a week or so of work, but what you're seeing here is rings of images from where the spacecraft acquired images. And so as I scroll around on this tab here, you can see, clicking on any one of the images, you see that image overlaid on that 3D model. So again, you're getting that 2D context in that 3D world. So again, really early prototypes here, but we really want to help the Hayabusa 2 mission as it's approaching the Ryugu asteroid, landing its rover assets and bringing asteroid samples back to help them with the ground operations there. So let me go back to the slides here. So, you know, today we talked a little bit about how we're taking these limited data sets, these 2D images, and recreating them in an immersive world to change the way that we do storytelling, essentially, on Mars. But what's the future here, right? The next rover we're sending up is 2020, in the year 2020. And on that rover, there's one new asset, right? We've got the Mars helicopter. And this will be the first interspatial aerial vehicle. It's got the 2-meter wingspan, 1 kilo payload, and it will be a companion for the rover and help it scout out potential sites. So for the first time, we're not only going to get the first-person view of the rover, but also get that third-person view. And so as, you know, engineers, as operators, we're super excited to think about that combined user case of how we can even expand the view of what we already have. Moving even further out, we're going to go to places, we're going to send humans to Mars, right? Whether that's NASA or SpaceX or the Chinese or someone in this room, we're going to get there. And when we do, this time, you know, the whole world's going to be watching, but this time we won't be glued to our TV screens. It won't just be the scientists or the engineers or the astronauts that get to go to Mars, because we'll all be able to join along virtually and welcome them in the new era of space exploration. Thank you.
All right, thank you, Victor. Just as a reminder, please go ahead and fill out those questions on our website. Because again, you guys own the audience, you guys own the conference, you guys drive it. So let's start with one of the questions that we have from today's audience. So are there any high-value areas on Mars that we haven't mapped yet? What's of interest to you guys?
There's a lot of, we haven't picked a landing site yet for 2020. We've got the InSight seismic, lander that's happening, I think the day after Thanksgiving. So that's happening next month that we're super excited about. We want to drill into the core of Mars and figure out, is there still activity?
Right.
That's exciting. There's just so much more to explore, right? We've hit, 5, 6 points.
And remind us the lifetime of the landers, of the rovers that we have up there.
Yeah, I think Opportunity's been there some 14, 15 years now.
Right.
Back in 2004, 2000 or so, that's when we landed. Curiosity's still going strong. Landed in 2012, it's been there for 6 years. And after InSight, it'll be 2020. And hopefully that'll go on for a while. It's going to be the first rover, first of a series of missions to target sample return. Mm-hmm. Right? It's going to be able to deposit caches on Mars for a future mission to collect and return to Earth. Excellent.
Very cool. Are there efforts to build gaming into browser experience to engage a broad population with this really cool technology?
Yeah, so we've already done that, right? We've got Access Mars, which is a very interactive Mars experience. We've got Spacecraft AR, which is more on the spacecraft side of things. If you take your phone, an Android phone, you can kind of place your spacecraft, take selfies with it, and learn about sort of the missions along the way. These new platforms are not only engaging our scientists and engineers, but we're building these experiences that are so tangible that everyone should be able to share in that.
Absolutely. They're, and obviously very inspirational for the next generation. I remember doing something like this when I was in school around the some of the Martian images that had come back, and obviously, well, and here I am today. So thank you for doing what you do. Of course. Can you tell us a little bit more about some of the augmented reality that you're working on? Some of the ideas going forward?
So talk about today, mostly focus on operations on Mars. We're doing a lot of work also in the formulation, design, and assembly phases as well. So we have a tool called Protospace, which we didn't talk about today. It's the ability to look at CAD at full fidelity in the same environment, right? So if we're all wearing headsets or we have our phones out, we can see the spacecraft in front of us and we can work on it collectively, right? And the magic for our tool, like the magic in here, is that we have this pipeline that's able to optimize that full fidelity model and render it on a mobile device. And we have also had sessions where we've, multiple agencies across the world being able to focus on the same model. So we're using that on almost all of our flight missions, Europa 2020, SWAT, Sentinel-6, a lot of the formulation programs, and working with HEO and some of the human flight programs to see if we can use this capability to augment procedures. Right? We sent 2 of these augmented reality devices to the space station a few years ago to really try to increase the output of the astronauts. Right? If they're having trouble with a procedure, if they need real-time support, they can dial into the ground. The ground can virtually reach out into the 3D world and annotate that world with models, with diagrams, and to really kind of give that first-person assist.
That is very, very cool. How are HoloLens and Microsoft involved in this work? Obviously, you mentioned your collaboration with Google. How are you reaching out to other tech companies to incorporate their backgrounds? Yeah,
one of our kind of pillars of the work that we do in the OpsLab is that we focus heavily on commercial partnerships. We value the capabilities we can do in-house, but we oftentimes value the capabilities outside even more. And so we look at what the best in class in industry is, and sometimes they're not released. Right? So our partnership with Microsoft HoloLens occurred many years before the public saw it, and that is what enabled a lot of these things to happen. Right? Shipping the HoloLens to the space station in less than 6 months of certification, being able to be a launch partner for a lot of these companies, and sharing in a lot of the development costs. Right? NASA can only afford so much, but these other companies have a lot of extra funding, and to find these win-win scenarios. And so, talking about sourcing to other industries, have you engaged in crowdsourcing to support either the development of this or the analysis of what you're finding on Mars? How are you engaging the public in that sense? Yeah, I mean, citizen science is always a big topic, right? The challenge is always trying to figure out the right engagement level that brings value to the mission, but also interest to the person doing it. So there's things to think about, areas of crater counting, rock counting. The other area where we include the public as much as we can is we try to open source a lot of this technology. We're working on, for example, open sourcing the Mars terrain that you saw so that people can take that, ingest it into their games or their experiences or their simulations, and in that way share in the creation of a lot of this media. Excellent. So we saw, obviously, the Mars images. We saw the Hayabusa representations that you're still working on, clearly. Yep. Any thoughts about about using the same concept on the moon or on other planets? What's the next step? Absolutely, yeah. We have ideas about how we can enable a more co-presence, not only on station but for future gateway. When there's no one there, or even when there's a few people there, how can we map that world in real time and kind of get that sense that I'm here or you're here or anyone can be there? We're working with NASA missions like Basalt and Finesse and other analogs here on Earth to study lava tubes or Mars analogs to do the same thing, right? Can you map out the world and give the EVA scientists or engineers a sort of pre-visualization before they go exercise? And that saves a lot of time, reduces a lot of risk, and I think over time is going to be able to output a lot of more valuable scientific data.
So, you know, we're talking about the use of AR to look at the rover. Is there anything that once you've gotten the rover on Mars, you've decided, well, I wish we had done that a little bit differently, especially based on what I see here? Yeah. How would you have designed it? Now, of course, hindsight is always 20/20. How would you design it differently?
You know, we're a relatively new lab. You know, we're 10 years or so. I think we were called the OpsLab because we used to be focused on operations, and now with a lot of these technologies, we're getting earlier and earlier influence in the missions, right, in formulation and design. I think ultimately what would be really impactful is working with the sensor teams, the instrument teams, the camera teams to figure out, are there new types of data sets or new types of chipsets that would enable us to send more data back or send more compressed data or more optimized or pre-configured data back so that we can even build up an even more valuable visualization for folks.
Would you, my question for you, is there anything that you see in this technology that you see as maybe as a perceived risk? Do you think there could ever be overdependence on something like this? Something that you miss? What's the downside? This is too cool.
Yeah.
There's got to be a hitch.
I think for most of the work that we've done is always backward compatible. So there's always the more analog way of investigating this data. There's more the traditional or legacy way of figuring out where they are and what they want to do. We're not replacing their work directly, but we're definitely augmenting and improving the timeline. You know, the previous mission we had about 11 hours to operate the Mars rover before the data comes back. We have 11 hours before we have to send new data back. For the next mission, 2020, we want to compress that timeline down to 5 hours, right? So that's more than 50%. And tools like this is what's going to make that possible, right? In the next rover mission, we're going to be able to give the scientists more and more capability. They're going to be able to see the reachability zones of the rover, the coverages, the joint limits, some of the things that only the engineers got to see to really reduce that back and forth between, here I want to go to all 100 different things, and the engineers coming back saying, you can't do that because of A, B, C, D, E. Yeah.
Great. Wonderful. Victor, thanks so much for your time and your talk.
Thank you very much.
Round of applause for Victor.